send you the request. So just approve them. No? Okay,
Yes, sir. Yes.
one person, maybe among the students or among the TAs whose connection is good, he has to take the responsibility of to download the lectures. So anyone among the students, I will allow you to download.
Sir, I can do that.
Yes, just tell me the name.
Devesh Govind.
Devesh Govind. Okay. Do you need any kind of permission, or it's you can do it? Just check.
Sir, I guess everyone can do it.
Oh, fine. So, but yeah, that's true. Everyone can do it, but then I am giving you this responsibility. Okay, Devesh.
Yes,
And
sir.
then later on, you can. No, later on means after this, maybe today night, you can upload it somewhere and share it with your friends. Okay. From the
Yes, sir.
next class, I'll assign it to a TA so that it will be always shared by TA, the downloaded lectures. Because I am not going to download because there are so many things on my laptop, and there are so many lectures that I can't keep this database. So I guess either a student or TA. So, what about your internet connection and space
So
in your
it's
laptop? It's fine.
it's fine. It's fine, sir.
So
Yes.
what you need to do that, let's say you download today's lecture, you record today's lecture,
Okay, sir.
uh, make a separate Gmail account, okay,
Okay, sir. Hmm.
and so that you have a lot of space in Google Drive, and then you
Hmm.
share it with that link on MS Teams itself. And once that is
Acha.
done, if you want, you can delete that file, no problem. Once it is accessed, so maybe after two
Sir,
three days, yeah,
sir, you can do it on MS Teams also. Means you can make one file
yeah,
and you can
true. I
upload
mean,
it
fine,
there.
fine, no problem. So that TA will do, okay.
Okay, sir.
Yeah, because I want to focus on what I need to teach rather than this uploading and all this. So that TA will take care. So Savik, you can upload it there also on MS Teams. I'll tell you how.
Okay, sir.
Okay.
Okay. Okay, sir.
And
Okay, sir.
once that file is on MS Teams, it means that
Hmm.
that is on the server of MS Teams. So you can delete it from your computer, I mean desktop or laptop, whatever you have. Okay.
Okay, sir.
So that
Okay, sir.
your space will not be flooded with these lecture,
Hmm.
video lectures. Okay, I think most of the people are here, so we can start. I don't see Amar. Amar is our third tier. So we have three tier in this course, and they will help us to, to conduct this coursework smoothly. Because without TA, it becomes very difficult. Now, I have a request for all three TAs that please
Yes.
listen the lectures carefully, because while checking the copies, I will be needing your help. Okay, because
Okay, sir.
checking so many copies without your help, it's impossible.
Okay,
So
sir.
just follow the lectures. You don't need to solve any assignment or anything. But if you'll follow the
Okay.
lectures, then I can always explain you the solution of the class test, and then we can do the evaluation together. Okay.
Okay, sir.
Sure, sir.
Yeah, great. Okay. Now, what else? That's all. Okay. I think we can start. So today is the introductory lecture. Let me. So Deves, you can start recording now. Huh? Now I'm sharing the uh, slides.
Yes, sir. The recording
Yeah.
was started long ago.
Okay, fine. And before we start, feel free to stop me. All of you, anyone can stop me. Okay. If any, see, remember this thermodynamics is very interesting and very fundamental course, and it's you can implement the concept in any, not only in engineering, in economics, in finance, anywhere. So this concept is really, really important for you. I mean, whatever we are going to learn in this subject. So it's so if you will not stop me, it's your fault. Okay. So because see, otherwise I cannot go to each one and ask you whether this concept is clear or not, whether you got it or not. So that way it's not going to work. We all have seen the bitter experience of this online teaching mode, and this online teaching can be successful only if you participate. If you will not ask, I will assume that okay, you got it. See, sometimes what happens that 20% of the people are getting everything in the class, and rest 80%, some of them are just ignoring, some of them are unable to get the concept in this online mode. So the only solution is you stop me. Okay. And no question is a silly question. Remember, if you don't know, it's a difficult question for you. You have to clear your doubt. So that's not all. I mean, that is the only way I can help you. Okay. So I want everyone to participate. I mean, and before going to the course, remember that I don't believe much on marks. I believe that if you learn something from this course, which you can implement in real life, then only that is the real purpose of any subject. Okay, so try to understand the concept. Don't I mean, not try to learn only to score in the exam. In fact, try to internalize it. Then you will enjoy the course. Okay. So I know that you have already a background of thermodynamics because for before coming here you have appeared in JE and you have a rough idea of what is thermodynamics. Okay, very rough. In fact, a very little. Whatever you have done in for your JE preparation, that is a small uh, percentage of what we are going to cover. So let me share the PPT. So before we proceed, remember that many times people don't remember the course name or course number. So this CH21008, Chemical Engineering Thermodynamics. Anyone can respond that whenever I am not audible, just respond me I am not audible. There was, you can hear me properly, right?
Yes, sir.
Perfect. Okay. So, well, I have put some animations, just to motivate you. We will see all these stuff one by one. For example, you can see that there is an animation of how an engine works. On the right hand side, you see this Carnot cycle, a PV diagram, and the actual process. Then this is simple, compression and expansion of a gas. Bottom left, and bottom right, you see this how these two gaseous molecule mix with each other. These all stuff are related to thermodynamics. And remember that in our day-to-day life, most of the activities are somehow related to thermodynamics. So this is one of the most fundamental and very important subject. Okay. And later on you will realize that whatever concepts we are going to learn in this subject, you can implement it in any field, believe me. Okay. Because see, remember there are two ways to learn this subject or to approach this subject. One is classical way, which we are going to cover. That is the content of this course. And another one is a statistical way, which is not in the course curriculum. And from both approach, you reach to the same conclusion. And that conclusion is inferred from the nature. Okay. Whatever laws, probably you know the first law of thermodynamics. And of course, there is second law, third law. So why we say it law, anyone? Any idea? What does it mean by law? Yeah.
Because it is universally true.
That's true, but there are so many, there are so many facts which are universally true. Law means, so why you call Newton's first law? Whereas there are some theorems. There is a law, there is a theorem. Any difference you see in this?
So you cannot prove a law.
Yeah, you cannot prove a law. Law is from nature. We have observed the nature for a longer duration, and then you figure out that there is something unique, let's say, in different processes. And that unique observation, we name it as law. For example, Newton's first law of thermodynamics, second law of thermodynamics. Okay. So what I was saying that either from classical way, I will tell you what is classical. What we are going to study is a classical way of thermodynamics, and there is a statistical way. From both way, you will reach to the same conclusion, which is inferred by these laws, thermodynamics laws. Okay. Yeah. So let's start with some. So that is the overall, philosophy of this course. That, but I elaborate on this. So before I tell you something, let me ask you a few questions. Huh? So when you have a cup of tea, hot cup of tea, what happens? Anyone?
It radiates heat.
It radiates heat, or we can say that heat gets transmitted from or transferred from this hot cup of tea to the environment, right? Ambient.
Yes, sir.
Right? So the heat flow is from hot to cold body or whatever you say. If there are two systems, if you assume that cup of tea is a system and rest is surrounding. Heat is going from system to surrounding. Okay. And then the tea cools down and it attains the temperature of the ambience. So can we revert this process? Like, can we revert back? That we can extract the heat from the environment and we can heat up the tea.
If the temperature
We need
difference
to do
is
additional work.
reverse.
Sorry. Okay.
Yes,
How do you
we
know
can.
we need to
We
add
need to
some
do-
work? Yes, someone said we need to do some work, right? You are right.
Yes, sir.
So have you read it somewhere?
So that we usually study, that is concept of refrigerator and all.
True. That is concept of refrigerator. Very good. But it has a more generic name in thermodynamics. It's a second law of thermodynamics. Okay. You are
So
right.
by inverting the potentials, total potential energy of the surrounding to be more.
Well, the simple thing is that what I mean to say is that if you want to transfer heat from a low temperature body to high temperature body, you have to do some work. It means that that process is not feasible, right?
Yes, sir.
So basically, the cooling process of a cup of tea is a feasible process, whereas reversible, sorry, not reversible, whereas the just opposite process is not feasible. Okay, let's take another example. When you mix two gases, so let's say if you take a gas A and gas B, and if you mix it, and let's say there is a diaphragm between these two gases, and when you remove the diaphragm, these gases mixed with each other very well. So that's a feasible process. But if you think that the reverse process is also possible, means these gases will again get separated without any additional work, that is not possible. And that's why separation of any mixture needs energy. Means energy needs money. Okay. So mixing is a spontaneous process. For example, mixing of two liquid, mixing of two gases. On the other hand, separation is not feasible. It's not a spontaneous process. Okay, you have to do some additional work in order to do that. So, in thermodynamics, what we are going to learn, or we are going to see what is the criteria for a feasibility of a process. Okay, remember this one. So, this we are going to learn feasibility of a process. Okay, what else? So, can anyone tell how our body works? Like, we eat food and then what happens? Maybe let me see the name of participants so that we can start interacting. Today's first class. It's an introductory class, so I can use this class to identify, to know you also, few of you. Gradually, I will come to know all of you. Although it's difficult to know everyone in this online mode, in class it becomes very easy, but that's fine. So where I can go to participants, yeah. Okay, so Abhishek.
Yes, sir.
Yeah, Abhishek Purohit. So Abhishek Kumar is also fine, no problem. So Abhishek, what do you think? How our body works? Why we eat food? If you
Like when we eat food, it is like dissociated in glucose, and then it releases
so
some
there are
ATP.
some molecular bonds which break, right?
Yes, sir.
So what happens then when it breaks?
It releases some ATP energy.
So heat
our
energy.
body.
It's a heat energy, let's say. Okay.
Yes.
It's a heat energy basically. Simply you can say it's a heat energy. So when what happens when this heat? So how this heat energy helps?
In our movement, in our body
So
functions.
and that's why if you realize in winter season or in a very cold day, you feel very lazy and you don't want to do anything. So basically your muscles need heat energy. Once the muscles temperature is high, then you can move it easily. So Abhishek, can you identify what is happening here? What is getting converted into what?
In which diagram, sir?
No, not diagram. In our body. Yeah.
Like
Can you identify?
glucose that we
So in broader sense, you are right. In broader sense, what I mean to say is that basically this is the heat which is getting converted into work in our body, right?
Yes.
we get this heat from the food because the molecules break and then heat energy gets released, and then this heat energy is getting converted into work, any kind of work, like either I am speaking or you are moving your body parts. So basically conversion of heat into work. You know how a bullet works? I have put that animation, if you can see. In bullet also what happens that whatever this gunpowder there is explosion in this gunpowder, and there is enormous pressure increase, due to which there is a sudden expansion of the gas which pushes the bullet. So here you can see that we are using the heat energy, or we are converting the heat energy into mechanical energy, basically kinetic energy. So this is heat is going to work. Let's see another example. What will happen? So let's say another participants. So now I know Abhishek, I know Deves. Let's say I'll talk to Aditya. You can hear me, Aditya Agrawal? There are so many Aditya, three Aditya.
Yes, sir, I can hear you.
Yeah, Aditya. So Aditya, if you can see this. So what will happen? Tell me, if you take a stirrer in a beaker and there is a water or any other liquid, and you stir it very vigorously, what will happen?
So the temperature will rise
Yes.
because we are
Another
doing some
example
work
that you
on
will
it.
rub your hand, then also, the temperature between the palm or upper palm gets increased, right?
Yes, sir.
Okay. Can you see the example on the bottom left? What is happening here?
So the steam,
So it's a heat engine, you are right.
yeah.
So we are making steam using heat, right?
Yes, sir.
And then this steam expands, and then we convert this translation motion into rotatory motion. That is the overall concept of heat engine, right?
Yes, sir.
So here what is happening? Heat to work or work to heat? Both. In example 1, it's work to heat, right?
Yes, sir.
On the other hand, in heat engine, it's heat to work, right?
Yes, sir. So it can
So
be
that-
work to heat also. Like,
Yeah, work to heat. This is no. The second one,
yes, sir. The second one.
heat engine is heat to work. Na? You are giving the heat and you are getting work, right?
Yeah, but the engine is rotating the wheel, so in this process, heat will also be generated, I think.
No, ignore that thing. I mean, don't go into so much detailed. Like you are talking about the friction and all such stuff, right?
Yes,
Yeah. For the moment, just ignore that. I mean, see it in a very naive way. Don't go to so much details. On a roughly, we can, if you ignore those losses, we can say that heat is getting converted into work, right?
Yes, sir.
So that defines the second goal of this subject. That what we are going to learn is interconvertibility of heat and work. We will see what is heat, what is work. The history is very, very interesting of heat. You will be amazed. Okay. So that is so we said feasibility of a process. Now we are saying interconvertibility of heat and work. That is the second important stuff which we cover in this subject. Third one is, so before we go to third one, let me see. So if you have, let's say, let me see with whom I can interact. So Aditya Agrawal, I know. Now two other Aditya are thinking that there will be some gap. So it's a big relief for them. Akhil Nama.
Yes,
Akhil, you can hear me? Yeah. Akhil, so let's say you have a container, okay, filled with water. I mean, partially filled with water, okay? And then you cover it from the top so that there is some vacant space in the container, right? And then you start boiling it and measure the pressure of that top part. So what will happen to the pressure?
sir, it will increase like
Up to what point?
till it becomes equal to the atmospheric pressure, external pressure.
What we call saturation pressure.
Yes, sir.
Okay. So why after that what happens? Why it doesn't go further?
Sir, like pressure equates on the both sides, so it
No,
won't
that's true.
increase.
But can you elaborate it on in a more fundamental way?
Since the lid is open, it is connected to atmosphere. If the lid was totally closed, pressure will increase. Like if
See,
it
Akhil, see what is happening that molecules are, when you provide the energy to the molecules, liquid molecules, it try to get away from this, like it gets energy, it goes to the vapor phase, right? That is process one. Okay.
yes,
Another process is just the reverse process. Like molecules are also hitting this water surface and they are getting condensed. Okay.
yes, sir.
So initially process one is dominating. But later on, as this will progress, both process 1 and process 2 will be happening at equal rate. That is called, so after that, you will not see any change, right?
Yes, sir.
So that is called equilibrium, right?
Yes, sir.
Another such example you can see in the chemical reactions. If it's a reversible reaction, let's say, for example, here I have taken this Fe3 plus and this thiocyanate ion, CNS. So it's not like that all the iron and anion will be consumed, okay, or what you call ligand will be consumed. In any reversible reaction, all the reactants will not be consumed. The reaction will take place only up to certain extent when the rate of forward reaction becomes equal to rate of backward reaction. That point is called equilibrium. After that, you will not see any change. So in
Yes, sir.
thermodynamics, yeah, thanks. Okay. So in thermodynamics, we
Sir.
also, yes, please.
Sir, if the lid is closed, then the pressure in the container will be the
Yeah.
function of the temperature of the liquid.
Yes,
Means,
of course. But then if you don't change the temperature, in that sense, so for every temperature, there is a saturation pressure.
matlab, sir, what I want to say is that the temperature
Oh, see
in the container
that
may
depends.
not be equal to the atmospheric pressure.
That depends. If you put what you call that, mm, if you put something like a coating through due to which the heat cannot go out, in that case, temperature will also.
Adiabatic container means if we have the
Yeah, adiabatic container. Yeah, adiabatic wall if you put, true, right? So it depends. I'm just roughly trying to explain that equilibrium. Okay, what is equilibrium? I mean that's the thing which you're asking. It's a more detailed, and I mean there are different conditions. It can be isothermal, it can be adiabatic, right? This heating of this thing. Okay. Hello.
Yes, sir.
Yeah, am I clear? I mean, what you
Yes,
said is
sir.
also right. I'm just roughly explaining. We are not going into the detail right now, at least. Okay. My only purpose was to motivate you that there is something called equilibrium. Okay. What will happen if you take a closed container, if you take a adiabatic wall, or if we take a thermal wall or diathermal wall? That we will see. See, if you take adiabatic wall, then of course temperature will increase. It's not going to remain constant. Okay.
Yes, sir.
Yeah. And for every temperature, there is a saturation pressure. Okay. So we will see this experiment, how we measure the saturation pressure. In that, there we will see that whether we should keep it closed container, or what does it mean by when the pressure becomes equal to atmospheric pressure. All these things we will see in detail. Okay. But the bottom line is that the way we define saturation pressure, it's nothing but the pressure at equilibrium in vapor phase. That is called saturation pressure. Okay. Okay, so three things. Now let's summarize this. What we are going to learn in thermodynamics: energy and its transformation, basically heat and work, most of the time. Okay. Second, feasibility of a process, and third, equilibrium processes or extent of change. So basically, as I told you, thermodynamics mainly deals with interconvertibility of heat and work and the properties of the system in equilibrium. Okay. well, in equilibrium, it's not very strict. But yeah, most of the time in thermodynamics, we say that it's a quasi-equilibrium state. So that's why I have put this word, properties of system in equilibrium. If a system is not in equilibrium, then heat transfer comes in, like what is called rate of heat transfer. Okay. So most of the time we'll see that we assume that it's a quasi-equilibrium state. Okay. And then remember, this thermodynamics is an inductive science. Now it has become so broad. I mean, its concepts are so generic that you can implement it in other fields also, as I already said. So remember these 3 points. That will be our agenda for this subject. That heat work convertibility, and then feasibility, and then equilibrium of the process. Remember, as we discussed, that all these laws which we are going to learn in this subject, they are mainly based on experimental observation over a very long time, and not only one scientist, by many scientists, okay, in different corners of the world. And then today, now these rules are, I mean, all these observations are unified in the form of these 3 laws, which we are going to learn, laws of thermodynamics. Okay, so you cannot prove them. Okay, you can formalize them. You can unify various observations. Okay, and the validity of these various laws lies in agreement between experimental results and the prediction made by these. Whatever law you are defining, let's say from you have 10 observations and you define the law, and then you implement the law for the 11th observation, and if it works, then your law is right. That's how science evolves. Science, or whatever you say, applied science, engineering. Okay. So there are 2 approaches, macroscopic and microscopic. It's also called statistical. What we are going to see is macroscopic. Many times we call it classical thermodynamics, because the observations are based on the and our laws are based on the macroscopic quantities or macroscopic observation. We'll see. Microscopic means the simplest example of microscopic approach is what we have already learned during your JEE preparation. Anyone can guess? Anything in thermodynamics you have learned which is microscopic or statistical? Well, let's say microscopic.
Kinetic theory of gases.
Kinetic theory of gases. Very good. So that is another approach. Okay. And in fact, there is a separate branch on this statistical thermodynamics. It's very involved, very deep. Very deep. There you have to first understand the true meaning of entropy, then only you can proceed. The meaning of entropy which we know, or which you know at your school level, or even after this course, is very preliminary. In order to get the real feel of entropy, so this whole entropy defines this microscopic approach. Okay. What we are going to learn is macroscopic approach. So, as I told you, these are laws of nature, and that's why it becomes very important for us at least to at least have a superficial knowledge of such kind of laws of nature, because these laws of nature dictate our life. Okay. See this, if you see the human history, so let's go to history. I mean, this is the first class. It's very important that from where this all stuff started, like what we know today as thermodynamics, from where it started. See, if you see the human history, from the very beginning, we human beings tried to convert heat into work. Either purposefully or by default. Our body is a perfect example of heat is getting converted into work, or otherwise also. For example, you see from 1680, what you can say, that scientific research has started on this stuff. Like you see this in 1680, this guy Huygens fabricated a piston engine powered by gunpowder. Later on, people tried steam also, you can say, in 1690. And then there was continuous ongoing research on this, how we can convert it into work. And then finally in 1769, this James Watt came up with this steam engine. Okay, so now that's why, the unit of power is watt. So in the honor of James Watt, we know that the unit of power is watt. Okay. And then later on, people have worked on this his design, and then they modified it. So it was ongoing research. Now we don't use steam engine, but but this quest is not. This quest is really old. Like,
So you are not audible.
Sir, you are on mute.
Sir is not on mute. I guess sir is not saying anything.
Silent treatment.
now you can hear me. There was some internet problem.
Yes, we can hear you now.
Thanks. Yes, Megha, problem is sorted out. I got your call. So somehow there was some problem with internet connection. Okay. So let me share it again. Yeah. So what I was saying that's also this heat into work. People have tried a lot, and then eventually this steam engine came in the picture, and later on you know that today we have this electric engine. Okay. You know, today when you learn this subject thermodynamics, it seems very easy that what a big deal in converting heat into work or work into it. It's fine. It's so obvious. But believe me, before Joule, it was not so obvious. Okay. So I'll tell you why. It has a very nice history that why it was not so obvious. So after Joule, people start formalizing that whether we can convert into heat into work or not, and such kind of stuff. This interconvertibility of heat and work. Okay. So Joule, yes. Someone's background noise. Yeah. So it was the Joule's experimental breakthrough, which leads to, or which led to this first law of thermodynamics. We'll see how. So when we'll do the first law of thermodynamics, we'll start with this Joule's experiment. Okay. So basically, if you'll see, the main contributor of first law was James Joule. Later on, this Clausius formalized this statement, or you can say he has extended what Joule did theoretically, or he has given a more generic statement about first law. I think first law you have seen in during your JEE in form of internal energy, work, and heat, right?
Yes, sir.
Yeah, but we'll see more we'll see more generic way. Okay, so what we know as first law, it got formalized between 1843 to 1850. Okay, so Joule has a very important contribution. We'll see. I have put this diagram for a purpose. I will not elaborate it, or I will not reveal about this diagram here. I will reveal it when we will do the first law of thermodynamics. I'm sure many of you you are aware of also about this experiment. This experiment is very simple, but it has a very nice history. Okay, and that I'm sure you will like that story when I will tell you that story in the next class. Then after first law, this very this Sadi Carnot was a French engineer, and you see at very early age he established this law. Basically, he was an engineer and he was working on heat engines, and then he came up with this Carnot theorem. And he was not knowing that this is the second law. He just defined it as a Carnot theorem. Then in 1854 Clausius came. Okay, he defined a different formulation, mathematical formulation. Eventually, and there are other statements also which I have not written here. There is something called Kelvin-Planck statement. So all the scientists in different part of world had different observations, or apparently, if you see, it looks that these are different observations. But later on, as this subject was evolving, today we know that this all can be very nicely combined in the form of second law of thermodynamics. And if you take one theorem, it can prove other theorem. Or if you take one statement, it can prove another statement. All these statements are identical, and that we will see in the second law of thermodynamics. So you see, to establish the second law of thermodynamics, or to unify these different observations, either by Carnot or by Clausius or by Kelvin-Planck, it took a long time, and that led to second law of thermodynamics. So I'm just sharing you it's not like that people, since there was a first law, people immediately defined second law. People were working on the practical problems. For example, this Carnot was working on the heat engines, and then he inferred something which is written here, that all irreversible heat engines between two reservoirs are less efficient than a Carnot engine operating between the same reservoirs. That we'll see in detail. So basically, my point is that he was not saying that this is the second law and it should follow the first law. He did his research independently. You see the timeline. Joule's experiment was 1843. Before that, Carnot established this Carnot theorem in 1824. Okay. So if you see history-wise, second law came first before first law. But we were not knowing in 1824 that this is the second law of thermodynamics. Then later on, in 1854, Clausius given another statement. Okay, and no one said this is a second law. Remember, they define it for their process. For example, Clausius said for a cyclic process, if it's a reversible process, then dou Q by T cyclic integral is 0, and if it's a irreversible process, it is less than 0. Later on, people tried to unify all these statements, and today we know that it's a second law. Okay. Then once there was first law, there was a second law. Okay. Then people realized that there should be, as we covered third law will come later. Then people realized that there should be zeroth law of thermodynamics also. Basically, we'll discuss on this. And this I will not focus on this part much. This I leave for you. So just try to Google it that what is the need of zeroth law of thermodynamics? Because it is very simple. You will find that the ultimate goal was to define temperature. What we should call temperature? What is temperature? So when people ask this question from thermodynamic perspective, they found that they have to define a zeroth law of thermodynamics. Okay. So this I leave for you. I will not discuss the zeroth law. Okay, then we know what is third law is basically nothing but it is originated from microscopic approach. Okay, and then many people contributed. For example, this James Clerk Maxwell, he discovered this distribution law of molecular velocities. It's a statistical approach. That's what we know as kinetic theory of gases. Okay. Then the most you can say that this the science of the main or the most significant scientist in thermodynamics was Gibbs. Gibbs free energy. He contributed significantly, and he made thermodynamics more generic, so that you can apply the thermodynamics in any complex process, not only heat and work. You can apply it for chemical reactions. You can apply it for solution thermodynamics. There is, mixing two liquids. So he make it more general so that you can apply it anywhere. And this whole chemical engineering established on the laws defined by Gibbs. Okay, so Gibbs made it basically what Gibbs did. Bridge both this macroscopic and microscopic approach. There was something called statistical approach. There is something called classical approach. He tried to bridge them. We won't be able to see that in this subject, because for that one has to learn the statistical thermodynamics or statistical mathematics. So, but just as an overview, I am sharing this with you. We'll end this lecture. We have 10 minutes. Okay. So later on, this Boltzmann defined this entropy of a system. Which has infinite number of constituents, like a gas. And there this is the bridge between macroscopic and microscopic. Why? Entropy is a macroscopic property which you can measure. You cannot measure. It means you can define it macroscopically. You cannot measure entropy directly. You can measure heat. Remember, you can measure temperature. So in form of heat and temperature, you can define this macroscopic property entropy. And what Boltzmann did, that he correlates this macroscopic property with microscopic features. What you see on the right hand side. Okay, this ln psi is nothing but this is the number of microscopic states, possible microscopic states or micro states. Okay, I'm not going to detail, but remember this was the bridge to correlate the macroscopic quantity which we can measure directly or indirectly. Entropy is an indirectly measured macroscopic property with the what you know as molecular details or microscopic details, which is theoretical. Because kinetic theory of gases, you can only imagine. You can never see that how molecules are hitting the wall. You can imagine a picture, then you define a model. For example, kinetic theory of gases is a model, and then you see that the prediction of this model whether it matches with my macroscopic measurement or not. So for example, let me ask someone, and then this concept will be more clear. Let's go to down. So Jyoti, you can hear me? Jyotiraditya, you can hear me?
Yes, sir.
Yeah. So my question
Yes,
to you
sir.
is that my question to you is that in kinetic theory of gases, right? You know that you have done it in JEE. So
Yes, sir.
which macroscopic property you can relate can be a bridge between this microscopic approach and macroscopic approach? Any guess? I think kinetic theory of gases, what you learn, like just say a few words and then I'll help you.
Temperature and kinetic energy relation.
That's true. Okay, temperature is also fine. Yeah, very good. So basically temperature we can measure macroscopically, right? That means using a thermometer, right?
Microscopically.
Macroscopically.
Yes. Yes, sir.
And then you have a microscopic picture. What you say? That this is the average kinetic energy of the molecules. They are in random motion. So that you are imagining. That you never know whether it is happening or not. Okay. That is your imagination, and based on that you have defined this model. Similarly, pressure also, right?
Yes, sir.
Because pressure also said that there is a bombardment on the wall of a container, and then according to Newton's second law, there is a force experienced by the wall, which we know as pressure, right?
Yes.
So pressure we can measure macroscopically, right? And we can
Yes,
always
sir.
correlate it with kinetic theory of gases. So kinetic theory of gases, it's the imagination, and that's what we call model. Okay. So that is statistical approach which we are trying to bridge with macroscopic measurable quantity. Okay. So with this, I think, yeah, thanks. So I think with this, I have given you enough background of this. From next class, we are going to start with first law. Now let me share the name. So the books which we are going to follow for next few classes is, in fact, most of the stuff is you can follow this thermodynamics and engineering approach by Sengel, and another book is engineering thermodynamics by YVC Rao. Okay. There is chemical engineering thermodynamics also, but I prefer this book to learn the first part of the thermodynamics. So I will teach you till mid-sem, and then after mid-sem, Professor Gargidas will teach you. He will teach you solution thermodynamics and few gas means a bit more complex systems. Or you can say more about fugacity, what is fugacity, or what is chemical potential, or all such stuff. That is the advanced version of thermodynamics, more specific to chemical engineering. And there is one more book. I will share the name of that book in after few classes when we will start. After finishing the second law, we will read something called availability, and there I will share the name of another book. That is a very nice book and a very fundamental book. For me, I have 50 marks out of 100, so I'll take 2 class tests, 25 marks each, announced. Okay. Anything from student side? I've spoken a lot, so yeah, anyone? So let me. Should I be a bit slow, or you think the pace is fine?
Sir, can it be made this way that like there'll be an optional third test, like best of 3, something like that?
Say, is it SETI? SETI, right?
Yes, Vardhan.
Vardhan, it's very difficult. See from teacher point of view, checking so many copies, 3 class tests, very difficult. Okay. See, anyway, Gargi ma'am will take 1 or 2 tests, right? So, like too many tests, then I have to check all the copies. So then I have to, I will get distracted in checking copies and evaluation. I don't like that thing much. I focus more on how much we can learn from each other. Is it okay, Vardhan? 2 is fine, I guess.
Yes, that's fine, sir.
Yeah. Yes, anyone? Kumari Bhavna? Everything is fine?
Yes, sir.
You are getting
It's
it?
fine, sir.
Great. Okay,
Yes, sir.
great. Yeah. Lalit?
Yes, sir.
Okay. Okay, guys. So, I mean, anytime you can stop me. Nitin Baghel? Nitin is trying to connect.
Excuse me, sir.
Yes, Nitin, you can hear me?
Sir, I'm not Nitin, but I just have a query.
Yes, please. Rishi.
Yes, sir. How will the test be conducted? Like, will it be in the Moodle platform or something else?
No. I see. Objective questions in this subject is very difficult. So maybe 1 hour, 2 or 3 questions.
Okay, sir.
I will make it bit lengthy, to be very frank, so that everyone will be busy with his or her paper, and there will not be disturbance from each other. That's all. So
Okay,
never
sir.
try to solve the whole paper in my exam. That is not possible. I am telling from the very beginning. Try to solve 70% of the paper, and that is done. With that, you will get a good grade. That's for sure. If you solve 70% of paper, because solving the whole paper is not possible, because I'll make it in such a way that everyone is busy with his or her question. I mean, exam. No disturbance from others. That's all. That is the only part where I will be bit not harsh, but that's the only way. Rishi, you got the point?
Yes,
I
sir.
have to
Yes.
make it bit lengthy. Don't worry. I am telling from the very beginning to all of you, don't worry about marks and grades. Try to focus on how much you can learn.
So, sir, it would be written paper.
Written. Yes, you write and then you upload, and then we will check. I will check with the help of PH. Okay. Any other doubt? Marks? Because in this subject, I don't think that there is any scope of presentation from a student side. And with so many students, it's difficult to handle. Anyone has any problem in listening me, or my pace is fast? Any comment on that, or I should keep this pace? What do you think?
Yeah, it's fine, sir.
Okay, perfect. So you have class after this class? I think no, right? Any class? I think 1 to 2:30 there is a break, right? 1 to 2. Okay,
Yes,
guys.
sir.
Then yeah. So see you tomorrow then. Okay. Who downloaded this recorded these lectures? Devis, right? For today.
Yes, sir.
Yeah. So Devis, just you share it with. I mean, you can upload it there itself, right? And then people will see that. Okay. Thank you. Thanks.
Thank you, sir.
Thank you, sir.
Okay.
Thank you, sir.
So I'll put the lecture link tomorrow. I'll post it.